Hello, and thank you for joining me today as we talk through calculating hydrogen and hydroxide concentrations. So we're going to calculate concentration of H and concentration of OH in regards to acids and bases. So your objectives, you'll be able to define pH and pOH, what those mean. We'll be able to calculate hydrogen and hydroxide concentrations from an initial aqueous concentration, and we'll understand what this Kw represents and be able to use it when calculating hydrogen and hydroxide concentrations. So let's get started. When we talk pH, pH measures the concentration of hydrogen ions. That's what it does. That's where the number comes from. And actually, more accurately, it's the difference in hydrogen concentration and hydroxide concentration of those ions. So pH measures the concentration of hydrogen ions. pOH measures the concentration of hydroxide ions, or the difference in hydroxide and hydrogen again, the backwards version. Both scales go from 0 to 14. And so typically we use the pH scale, but we can talk pOH as well. But both go from 0 to 14. On the pH scale, 0 means highly acidic, 7 means neutral, and 14 is highly basic or most basic. And we'll talk about kind of what that means. We'll go through some of those situations. But this is what we're looking at. If you have anywhere from 0 to 3 on the pH scale is a strong acid. 4 to 6 is a weak acid. Anything above 7, well, I guess 4 to 7 is a weak acid. Anything above 7, so 7-ish, to 10 is a weak alkali or a weak base. And then above 10 to 14 is your strong bases. So we'll talk through some of those as well. When we talk pH, we can write either pH or we can write P times concentration of H, because this letter P stands for a mathematical process. That it's actually the negative log. P means negative log. So when we calculate pH, we are actually taking the negative log of the hydrogen ions, concentration of hydrogen ions in that solution. And likewise, pOH is the negative log of the hydroxide concentration. So these two work inversely, but this is, P means negative log is all it means. So here's some examples that we look at pH. We don't really talk much with pOH, but it's there. And so some things that you're familiar with: gastric juice, so stomach acid, pH between 1 and 3. Lemons have pH between 2.2 and 2.4. We have vinegar. We have pops in here, so soft drinks. Your apples are acidic. Grapes, oranges, cherries, tomatoes, all of those. As you work up the scale, eventually you get to above 7, which is pure water. 7 is neutral. Blood is slightly basic. Eggs, seawater, and then milk is also slightly basic. Milk of magnesia is slightly basic. Regular milk is slightly acidic. And so when we look at these, we're looking for the concentration of hydrogen and hydroxide ions. And so we have scientists have concluded that if you take the concentration of hydrogen multiplied by the concentration of hydroxide ions, you should come to a value of 1 times 10 to the minus 14. And this number, they have given a term, we call it Kw. This is your water constant. So in normal water, in pure water, we have H2O. And we had talked that when H2O dissociates, it splits into H plus and OH negative. Or if we have two waters, it's H3O positive plus OH negative. Same situation. But this concentration here, so your molarity here, oops, that didn't work. Your molarity here multiplied by your molarity over here will give you a value of 1 times 10 to the minus 14th. So if I take concentration of H plus times my concentration of OH negative, I have to equal 1.0 times 10 to the negative 14th power. And that's what Kw represents. So this, we can calculate concentration of hydrogen by dividing hydroxide across. So we take Kw divided by OH. We can calculate hydroxide by dividing Kw by H plus. And when we talk exponents, you're going to have a lot of exponents here. To make calculations easy, you multiply the numbers. When you multiply numbers, you add exponents. If I take H times OH, I'm going to multiply these numbers. I'm going to add the exponents. If I divide numbers, when I take Kw divided by, you divide your numbers and then you subtract your exponents. But as far as exponents go, your exponent on hydrogen plus your exponent on hydroxide should equal negative 14. 10 to the negative 14th should be your final answer there. And so we'll practice this here right now. For example, a 1.0 times 10 to the minus 4th molar solution of HNO3 can be prepared for a lab experiment. Has been prepared. Calculate hydrogen and hydroxide concentrations for the solution. So we have HNO3. And when HNO3 dissociates, it's going to split into, actually, HNO3 is a strong acid, so we're just going to go this way. It's going to split into H plus OH negative. We know that we have 1.0 times 10 to the minus 4th molar HNO3. So I know this number is 1.0 times 10 to the minus 4th molar concentration here. Because my molar ratios are 1 to 1 to 1, I know that this concentration is going to be the same for hydrogen and the same for hydroxide. So I'm going to have a hydrogen concentration of 1.0. I'm going to have a hydrogen concentration of, and this shouldn't be, that shouldn't have been hydroxide. That should have been NO3. This should be NO3 negative. So I have 1.0 times 10 to the minus 4th molar hydrogen and 1.0 times 10 to the minus 4th nitrate. Okay, I'm worried about hydrogen right now. So because I know I split from HNO3 into H plus NO3 negative, my hydrogen concentration is going to be this value. So I know the concentration of H plus equals 1.0 times 10 to the minus 4th molar. I also want to find my hydroxide concentration. So concentration of hydroxide. Remember we talked in the last slide that if I take H plus times OH negative, I'm going to get my 1.0 times 10 to the minus 14. And this, unit-wise, this is molar squared, but that's not super important at this point. So we have concentrations times concentration equals this. So to get OH, I need to take, I'm going to take Kw and I'm going to divide it by my hydrogen concentration. So if I do that, I get concentration of OH negative is equal to 1.0 times 10 to the minus 14th over 1.0 times 10 to the minus 4. If I divide these two, remember on the last slide we said we divide the numbers, so I'm going to get 1 divided by 1 is still 1, so I still have 1.0 times 10, and because these are being divided, we're going to subtract this. So negative 14 minus a negative 4 is going to be 10 to the minus 10 molar. So those are going to be my two concentrations there, concentration of hydrogen and concentration of hydroxide. I will let you practice these. I do want to walk through the last one. So if you want to pause this quick, you can pause and practice. Remember your split, I guess. I'll just remind you up here. So if I do something like sulfuric acid doesn't completely dissociate second time, but for example purposes it'll work. Actually, let's do this. Let's undo that. If I have calcium chloride, when I split this, I get 1 calcium and I get 2 chlorides. So my concentration here, so if this is a concentration of 1.0 molar, because this is 1 to 1, this is also going to be 1.0 molar. Because this is 2 to 1, this is going to be 2.0 molar. So remember that as you work through these. If you want to pause this and practice these quick, I will show you the answers just now. So when you solve those, This is going to be your answers. If you don't get those, have questions, please ask. But I need to keep going. So here are some questions for you to close to. So I want to know, you should be able to answer, what is the mathematical expression of P? So what does P mean? What is hydrogen concentration times hydroxide concentration equal to? The number here is known as what? So the number in this question is known as what? What does POH mean? And if I take hydrogen, I want to know what is the hydrogen and hydroxide concentrations of 4.5 times 10 to the minus 4th molar barium hydroxide. Thank you for your time and attention. I wish you the best of luck, and we will continue this tomorrow.